I'm going to start recording. Okay. So I suppose if we're talking with people. Yeah, I'm recording. Yeah.
You didn't ask for my permission.
Yeah, I know. Yeah, but I record to a separate audio file, so I can just delete yours.
Okay. Does it?
What's that? It records each person to a separate audio file. So
just keep it 20 minutes.
Yeah. Yeah.
So I don't know. Yeah.
Okay. So
before you start, I'll introduce you.
Hey, for starters, should I run through the general way that GeoPIXE likes to work in that?
Yes.
Yeah.
I think you should, but maybe actually let's come up with a little schedule so it doesn't have to be in your head. So how long do you want to spend on that?
So I suppose I'll keep it to 20 minutes and we can edit the video down later to 20 minutes if we need to. But I suppose I will start by explaining the flow. So we start in the bottom left and we do this circle back up to the top.
Yep.
I'll talk about just importing the spectra, condensing it into one spectra, energy calibration, which we do. I mean, this is not going to take long. The fit will take a little bit more time, so I'll load up a previous one, select some things, and then the sort EVT files, and then I can go into the image and extracting separate parts and ways that we do that.
Yep. Okay.
Sound like a plan?
I'll prompt you then every 2 minutes or so whenever I think we should move on.
Yeah.
Does that sound? So there was overview of the flow, importing spectra, condensing all the spectra into one spectra, doing an energy calibration, and before you move on to the image analysis, what did you say? That's one of the
the fit.
Fit. That's right.
Yeah.
Cool.
Yeah. So I think this first stage won't take that long. Okay. Whenever you're ready.
Okay.
Were you going to introduce me?
Yeah, hang on.
Okay, sorry.
There it is. Okay. So, I'm David Flannery, and I'm on Zoom here with Michael Jones, who is our synchrotron-based micro X-ray fluorescence expert here at QUT, and he's going to run through how the beamline scientists and other users use a program called GeoPIXE to analyze the data that comes off the Australian synchrotron.
Good morning, or afternoon, I suppose. GeoPIXE is a software which we use to process X-ray fluorescence data. It can handle a lot of different inputs. At the Australian synchrotron, we use it to process the 384 element Maya fluorescence detector data. It works through a process of dynamic array matrix fitting. And I'll just run through quickly the basic process, and I suppose we'll go into some more details. So if you can see the bottom left window here, we have a window called Spectrum Display, and this is sort of where we start with GeoPIXE, importing the spectrum, doing some energy calibration, visualizing the spectrum, and we have counts and energy in KeV. And we sort of go in an anti-clockwise way around the screen. So the next one is X-ray spectrum fit, where we are selecting elements. We're doing some more background fitting, fitting things like Compton and elastic scatter. From then on up, we do which is called sort EVT files, and this is where we're taking the fit that we developed in the X-ray spectrum fit window and applying it to some energy versus time data files that come off the detector. So this sorts all the files sorts all the photon events according to the matrix that we fit it to. And then from there, we also have some flux parameters where we're putting in some conversions to quantitate the data. And there's a whole lot of other different options. And then we move on to the window where we get our final image, and there's some image processing things we can do in there. So we'll just quickly run through that process. So in the spectrum...
Before you do, Michael, could you take a step back for a moment and explain how this program is accessed. So this is not running on your local machine, is it?
So no, this is running on, if I move this window, you should be able to see on the Australian synchrotron computing infrastructure. So GeoPIXE is a software that is not a free software. It's written by some people at CSIRO, so CSIRO in Australia. And so it's the synchrotron provide it for users. So they have a number of licenses that users can access to analyze their data and process their data.
And so it runs on their computer infrastructure.
It runs on their cluster there, and I'm just logging into the desktop. And it's all based on IDL for some reason.
So imagine that keeps things relatively quick. It processes things quickly if it's running on a cluster. But are there any sides to
it does it a lot? Yeah, it does it a lot faster than when you run it on a local machine.
Are there any downsides to running it through a remote desktop like this, in your experience?
If you don't have a good connection to the remote desktop, it can be annoying. Otherwise, it's fine. The only tricky part is if you want to upload some specific files back to the system. But downloading them is easy, uploading them is not so easy, but this is mostly due to permissions and write protection on folders that they have.
Okay, thanks.
Yep. So we start with the spectrum display, and let's assume we've collected some data. The first thing we need to do is import some spectra. When we click on that, we have a lot of different options, and we're collecting synchrotron X-ray fluorescence, but we could also use this for PIXE data, for instance. And there's a huge list of detectors that have been coded up for it, and we're doing a Maya with corrected files. So this is just, we linearize the files as we save them. I can then select the files from a list, and this is just going in, and there's one that we want to have a look at, which is here. And here we have the data files from the folder. Each folder is a scan, and the files here are broken up into what's called a binary log file, and each one is a certain size. And here you can see this scan here, we collected 105 scans, and I can just sort them like this. I'm not going to import them all. I'm just going to import a subsection of them just because it will take forever. It then prompts me where I want to put them afterwards. Got a little folder called demo there. Now it's read the header files, and it has some parameters that it said. So we've got some preamp parameters, some dwells and things like this. Sometimes it doesn't manage to read them all. You can see it's missed the dwell parameter there. I can put that in, and I'm going to just say it will probably about 2 milliseconds, but we can see. I can also get this data from a preloaded spectrum file, or from a DA, or from an image file, which is we call a DAI, a dynamic array image. And then I can hit OK. And then it asks me for a pileup file, and I've got to explain what a pileup is here we have a window which is the amplitude of a detected photon event versus the time that photon event took to go through the system. And I can show this is all the detector elements, and I can just scroll through and show individual detector elements with this slider here, which is not working very well. Probably a downside of logging in. Oh, no, it's because I've got this window here open. It's not going to do it. But I'm going to select this one, which is a predefined one we have. And a throttle file is the next one that it asks for. And because we have a lot of backscatter in this detector, we actually throttle the Compton and elastic scatter, because we generally collect orders of magnitude more of that than for any individual element. And we just do this to save time. So we just collect between a certain energy range, we just collect 1 in 10 photon events, and we discard the rest. And then it's loading this up into the cluster and sorting these files and developing my spectrum from it. And this just takes a minute or two. And here we have all of the data that came out of the spectrum that I selected. You can see there's some mess over the top of it. I have a little button here that goes select, and I can select individual spectra. The button that I want to use now is called delete all X, Y, and T. So this has extracted from the spectrum not only the photon events, but it's also extracted the position and time files, which I don't really care about. And I can actually see here that this didn't apply the throttle correctly. So I'm just going to quickly get back and do that again, because else we'll run into some problems.
So those are, while you're doing that, in the spectrum display there, the data that looks like it's behind the fluorescence data, the little steps.
Yes.
Geometry that you're going to get rid of.
Yeah, that's the data that we have behind those steps is the position data and the time data. Also of interest, this data here, I can see this is the Compton scatter going up, and then it dips down by about an order of magnitude, and this is where the throttle hasn't been applied properly. So this is what I was talking about there. I did that on purpose so you could see what the throttle was like. So the throttle would be in there. And that should work, and we should now have that Compton looking much smoother across the top. It's done. Sometimes when you're not doing a huge amount, the cluster can take longer because it takes so much time to load it up and back down from the cluster.
Right.
When you're doing a big file, you get huge benefits. So there we go. Now we have the Compton, you can see back where it should be. I can delete that X, Y, and T data, and we can just see now our fluorescent spectrum. And now I can actually go to this time amplitude display and just give you a look at the throttle. So here's every individual detector element, and we can see we have a curve where we have what we assume are individual photon events, and then where we have lots of fluorescent data. So in the scatter, and usually around iron, for instance, we have events where the time is longer than the amplitude should be. So these are where we have multiple photon events that are overlapping at one energy. And we exclude them by just drawing a region of interest around this.
Interesting.
So we just draw a thing around here, and we say if it's outside of this box, it's more than one event. So we can tweak that as much as you want, and you can run through the individual elements with this and make sure you've got them all.
Cool.
So that's how we exclude pileup in GeoPIXE.
Would you be able to mash all of the detector elements together and draw one box, or is it?
Yes, you can. It's just generally easier to draw it over one and then see that it fits the others, because sometimes it blurs a bit too much when you have all of them there.
Okay.
But this is just very data dependent. The problem with fitting fluorescence data is it's generally pretty user intensive to do it really well. Now we have the spectrum here, and you can see if I just select one here, I can go down this and just show different what each different element collected.
Yep.
And so this is all this, but we display them all, and we have all of it here.
Can you show us some of the buttons you have down there that allow you to manipulate that window, or some of, I guess you'll go through it soon, but any of the operations that you would go through to look at different parts of the spectrum or display it differently? Yeah,
so at this point, I'm just going to display it how it is. Of course, when we get up to about 20 keV here, this is just mostly pileups that is sort of snuck in. We can hit the expand button, which will just expand the spectrum so we can just see what we want to see. For instance, like this. We also have a log lin button, so we can convert it into a linear scale and see that most of what we want is not a lot of counts. But typically we view it on a log scale, and we go from there. Calibrating the data can be tricky. We have a few different ways of doing that, and it's in, of course, calibrate here. I can just click on one here and just select, for instance, what I assume is iron K alpha, and let's just go for the elastic, which is at 18.5 kV. And what I can then do is just draw two lines and say that is where my iron K alpha should be, and that is where my elastic should be. And then I can just hit all, and that will just sort of move it. With a lot of spectra in there, it generally doesn't do a very good job. How we normally do the calibration is on a foil beforehand, and it's actually not too badly done coming off the detector at the moment. I can get all the energy cals from a spectrum that I've done previously. And if I can just find where we did the standards, I've got one here that I've got calibrated, and then this is just applying a calibration to every spectra. I'll show you another way to do it later when we get to it, but that's just one way of doing it, just with these two lines. And you can scroll through and calibrate every individual detector element. If you have one or two detector elements, that's easy. When you have 380, it takes forever, and you tend not to do it. Then what we do is we add the spectrum. So we don't want to fit all of these individually, so we just add them into one. So we add it into one.
So that instantaneously summed all of the spectra.
Yes. Yeah, and because all of the detector elements are at a different position, it applies a sort of a fudge factor based on the angle and the counts that each detector is sort of taking in. It does that mostly to the Compton scatter because it's going to be a different amount. So we've got one fitted spectra now, one summed spectra. And then what we want to do is we want to fit that spectra, obviously. At the moment, I can click on elements, but nothing is appearing. So I'll get rid of those, and I'll start where we have to actually start, which is...
So I noticed that you've got the different lines, the KLM,
yep,
KNL, and LNM, they're all color-coded. And as you click on those buttons, it cycles through the different lines.
Yeah, so if I assume I've got an M line of osmium, then I can just select just the M, for instance. If I'm not sure I've got K, or I'm not sure if I might have a K, I can select it back onto, with a right click, I can select it onto these green ones, which are question mark K. So this is thinking about maybe fitting a K line, whereas if I go to the green one, it's definitely trying to fit a K line to it.
But it won't fit it until you press a button, I imagine.
It won't fit it until I press several buttons.
And so if you saw a peak in that summed spectrum and you're wondering, hey, is that a chromium peak? How would you testing that?
How would I do that? I've got a little button here which says a question mark. And here I can go to two options. I can identify the element, or I can mark the element. Before I do that, there's another box down here which has got a drop down for different ones. So when I was on the energy calibrate window, this was on calibrate, which gives me two lines. I can also select then to identify line, and now I can drag a line across here and it will cycle through the elements that it thinks fit around about here.
That looks like a very useful little table there.
So that's quite useful because it's got all of them. It can get very confusing. I mean, this is, for instance, now I'm on the iron K beta 1 peak, and then I should be able to go up and find iron K beta K alpha 1, for instance. There it is. But you see there's a lot of other things really close.
Yeah. I wonder if it would be useful to have a condensed table with your most common elements. Didn't have all of these more obscure ones.
I think that would be good. The one that I tend not to use this one because there's just so many things so close. I tend to use mark element, and of course the program's buggy. So we go back to just mark element, and it gives me a periodic table. And here down the bottom, I can select K, L, or M, and I might as well just select all of them. And for instance, now I can click on an element and it shows me where the lines for iron will be. I can click on, for instance, platinum, and it shows here. It's got orange lines, which are the emission lines, and dotted blue lines, which are the excited lines. So we have to be above this energy to excite it, and then we get below this. For instance, if I go to one that's going to be close, for instance, molybdenum, I've got these lines here, which should appear here, but I'm not exciting these.
Mm-hmm.
It's too high in energy to excite. Again here as well. And then we get here and we're now exciting these photons. So that's helpful. And I usually have that one open if I'm fitting a sample for the first time. So now the fitting, there's a few things we have to do before we can fit something. And one of those ones is to determine the yields. And the yields is going to give us the expected fluorescent photon yields given a specific set of input parameters and sample parameters. So incident beam and sample parameters. I'm going to just run through the process of getting a new one. Another window launches up. Lots of windows always launch up. And I'm just going to select a previously made setup and run it through because it will take too long. What do we have here? Do you remember what this one is?
I believe this is so it's a clastic rock, probably quartz grains and some transition metals and other metals.
Okay. So let's call it quartz on glass for starters. So what we're doing is we're setting up what the matrix is, for instance. And you can see we have some detector parameters up here. So we're saying it's 18.5 keV. They're monochromatic photons. We're collecting it on a certain detector that it's positioned in this position, and I can show a little graphic will come up, which can show me what it actually looks like. So we have the beam going through to the target, and we're in the backscatter geometry. So that can be helpful for all sorts of things. It's an array detector, and then here we've got, so I suppose the top half is our incident parameters, and the bottom half is our sample. We have a target layer. We've said that we're 2 layers. We've got, we're defining layer 1, and layer 1 is our unknown. We're saying that layer 1 is 30 microns thick with a density of 2.648, I assume standard scientific units, and we've called it silicon dioxide. So we're saying this is 30 microns of quartz as a bulk sample matrix, of course, with other things in it. We can then go down to define layer 2, and layer 2 we can see we're now on 1 millimeter quartz glass. But we're saying that this is a known layer, so we're not trying to say that there's anything else in it. So this is our substrate, for instance. Yeah.
So once we've figured out what our matrix correction should be, are there any other tricks that you might employ to help you figure out what elements you have in your sample, or what some of those other peaks might be?
Yes. So this sample matrix is, we are not fitting this sample matrix. This is what we consider to be the bulk of the sample. And it's going to subtract this from everything that we have, and it will use this for 2 reasons. It will use it to fit a background to our data, and it will also use it to calculate and correct for self-absorption based on the angle of each detector element, which is going to be different depending on the thickness, and it will boost lighter elements more than heavier elements.
So this is something you would do before you even started to identify those peaks?
Yes, you actually have to do this before you start to identify the peaks. The program won't allow you to fit peaks onto nothing. So this is defining our background, and you'll see once I hit calculate yields, it'll quickly calculate based on the samples that we've put in, the detector and the parameters. And I'm just going to say, yes, we'll save that because that's where it was. And now we have a purple background line on our sample. I can close that. The purple is starting at 3 kV because that's what it's got here. We can see that this is not right, and we have stuff below it. So I'm going to change this lower energy range to about 1.8, which should maybe even a bit less than that. And you can see my purple line just continues on. And I'll just do it until we hit that line where we get a sharp drop off in the detection. a couple of buttons here that are default checked on, and I like to uncheck them. Cal on will try and calibrate the spectrum with respect to energy to fit the elements you've selected. Tail on will try and automatically fit a Compton tail, which I find does not a very good job. And full width half max will try and automatically fit a full width half max of the peaks. I'm not going to do any of that. Another interesting thing we have here is Q. And Q, if I click that box, converts from an incident flux to an expected fluorescent yield. So this is our calibration number, I suppose, that we're using to convert from incident flux to output numbers. Yeah. And we do this with a known sample first, and we fit that, and we adjust this number till we get the known concentrations that we have in that sample. And we have little wizards that do this for us. So now I've got my background, I can start to put elements on top, and we've already identified that we have iron, and as soon as I click iron, it now puts a fit on top of that. And it's just fitted those iron peaks that we identify when we click on iron. It also has got another little peak here, which is should be at about 3 kV less, which is a silicon escape peak. Yeah, so it automatically is calculating all those escape peaks as well.
Yeah. So in order to see where an escape peak would be, all you have to do is select the element you think it might be related to, and it'll show up there.
I can actually just go display silicon escapes.
Ooh, that's very cool.
We've got our silicon escape spectrum, I suppose. So this is just it's just a mirror of the spectrum shifted down in counts and down in energy.
Are there any other little tricks like that you might want to show us?
There are, but we'll get to them. And then what I'm doing now is just selecting elements. Generally, we have the elements contained in stainless steel because there's a lot of stainless steel around the chamber. And then I'm just going to go up in here, say we've probably got some calcium, not a lot, potassium. We have argon because the system's in air. Maybe not much of these lower elements here. Tiny little bump of silicon there, and maybe a tiny bump of aluminium. Arsenic, maybe no selenium, bromine, krypton. I'm just going to go through and fit some.
Yep.
And zirconium. And now I've got a whole lot fitted in. I'm missing something here, which will be titanium. And now I'm going to fit one, and it's just going to do its best job at fitting that. It's done not a too bad job. We can see we've fitted something here where there isn't. We've missed something here, and we've missed something here. So we probably might go, that sounds like it could be vanadium, which is a nice one to generally have as well. This one here, I think, was cobalt, didn't exist there. And that's gotten rid of that. And we probably have gallium in there. So now we've got a fit that looks kind of okay. We're now going to do a whole lot of fitting up here, and I'm just going to really quickly do that because that can be a bit of a problem.
Yep.
If I click on the advanced tab, I've got something called widths. I know that the widths are not 300 EV. And this is fitting it for where the manganese K alpha edge is as well. They're closer to 270, and this is based on basic detector parameters and things like that.
Looks like we have a lot of extra functionality in here to get that fit as good as it can be.
There's a lot, and I've got this one here, which I'm just going to quickly put some budget out a bit, which is also might be somewhat important, but this is just parameters which are changing the position of the Compton scatter and how it affects the fit. And you can spend a lifetime fitting this perfectly, and it's not always beneficial.
Okay.
But that looks, we'll say that looks great, and we're done. This little bit here, I'm not super fussed with. This is generally pile-ups that we haven't fitted. perfectly, I haven't excluded perfectly. We're missing a peak down there, which will be sulfur. And there we've got a reasonable fit, and I can go on forever doing this, but in the interest of time, we'll leave it there.
Yep.
What I then have to do is create what we call a DA matrix, which we're then going to use to sort our incident data. And there's a button here called Generate DA Matrix. So I'm going to click on that. I've got two options here. I've got a normal one or I've got a Zanes one. The Zanes one is not really important here, so we'll just go to the normal one. And then I click OK. It asks me where I want to save it. I'll save it with the file, which was 37050. And I'll save that. And now I've got a button here which is called P, which will show me all the peaks. And this is what we've fitted to our data.
So essentially, by creating that DA matrix file, you have generated a new corrected data set from which you will pull out the maps. Is that right?
So how we're actually generating an image is we are sorting energy versus time files through a matrix inversion process. So this is my inverting matrix, so to speak, that I've created.
Okay. Yep.
So I've essentially created a lookup table that says if the photon is here, then it belongs to this element.
Yep.
You can see there's huge overlap with everything throughout here. So it's actually taking ratios of known ratios of K alpha to K beta, K to M, these sort of things.
Right.
So saying we have a known number of, a known ratio. So if I have 2 K alpha ion photons, I need 1 K beta, for instance. And so it's making sure that all those numbers fit and are consistent throughout the fit.
Okay.
Yeah, so now we go up into this sort EVT window. And what we're going to do is we're going to put that file into the dynamic array analysis projection. And I've saved it, not in there. This has a horrible setup for just creating windows and folders for you. So we've got our dynamic array here. I'm going to save it in the output of demo again because I don't want to mess it up. I've got my calibration numbers here. I'm going to get them from the file that we used to calibrate our data in the first place. There's a couple of things you can put in, what sort of data it is, what the detector is. We can go flux here and it's pulled up our preamp sensitivity and our dwell, and we've got our conversion that was recreated from our standards. The scan, I can compress it however much I want. So if I've collected non-uniform scan data, so if I've sampled every 10 microns in Y and 2 microns in X, I can correct for that here. There's some device parameters, which is just for clearing a little border if you want to clear a border. So sometimes you overscan and you want to clear a border, for instance. You can do that here. We generally do that before we write the data anyway. Then I'm going to go my first file, and I'm going to go back and find the first file that I did, which was here, here, here. And when I click that, it's going to say, do I want to use these parameter automatically generated ones? Yes and yes. And it's pretty much saying, do you want to use the pileup and throttle that you used when you were collecting the data? And we make sure that we set that correctly so that, yes, we do want to do that. It's saving in the right place. Comments that we use to collect the data are now here, and the data, the sample number. And we have also, of course, the device. It's a Maya synchrotron, and we use the high mod to detect it. And this is just a few little things. We're clustering, and we've got another button here, which is flatten. And flatten we check on, which actually normalizes the data to the incident beam flux for that pixel. So it takes up for any variation in the flux. And we hit start, and this might take a minute to do because there's a lot of files in here.
Okay. While that's running,
Yes.
are there any other tricks in that spectrum display you think it's worth talking about, even if you can't press the buttons? What's the S button down there in on the bottom bar?
I can't remember. I haven't used it for a long time.
Okay, never mind about that one then.
There are the errors and the difference. If you click on errors, it will show you the calculated error for each
So
each point.
How does it calculate the error?
I think it does a numerical one, but I haven't really looked into it. But if you actually look at it, if we click it, the error appears to just be proportional to counts.
Mm-hmm. And the sort of one spectrum or detector element subtracted from another or something?
The difference, you mean?
Yeah, what's the difference?
The difference is the displayed spectra compared to your fitted spectra.
Right.
So sometimes it's very hard to see if you've done a good fit, and you can just show the difference between them. It'll highlight any differences quite clearly.
Yep.
And at some point with every fit like this, you get very diminishing returns very quickly.
Mm-hmm.
Yeah. But once we've got this image, which is coming along quite quickly, it's just got to get it all back off the cluster, and then we can go through some more exciting parts, I think.
Yep. Do you use the difference or residual display there very often?
I generally don't, because I'll show you what I generally do and find much more important and informative, I suppose, which is this. We now have our image. Because it's a weird program, it'll do all sorts of weird stuff when I rescale it. And what the first element that's shown is background, which essentially is those residuals or those unfitted parts. Ideally, you want this to be uniform. It's not in this case.
So residual would vary across the energy range. When you display the background map, is it just the sum of all of the residual counts?
Yeah, so there is energy information behind this, but we've now converted from energy space into pixel space. Mm-hmm. So I suppose energy is now encoded in this drop-down box for elements.
And the background, instead of representing the difference or residual at a certain peak position, it's just the whole spectrum summed together. Is that right?
It's in an XY, but it's the background in XY space rather than in energy space. Yeah, it's just taken the whole sum of the energy space background. Mm-hmm. Yep. Okay. In a perfect world, this would be perfectly flat, and we wouldn't have structure in it. That we have structure in it tells us that we've most likely missed something, and we've most likely mixed something in these spots where we see this distribution.
But only in certain areas. And so one of the things you might want to do, I guess, would be to sub-select one of those regions and fit for that region.
Yep, so I'll get to that in a second. What we've got, though, if I can just quickly scroll through, we've got our fits to all of our data, and it's just here displaying it as a percentage of the maximum value that we get. So, for instance, I'll move my mouse there. We've got argon, potassium, calcium, titanium, for instance, and we can see all of these maps. And of course, when you have a very bright spot, it swamps the signal, and so you can just move it down until you can see what it looks like.
Change the thresholds. Can you change the scaling? For example, make it a log color scale?
Yes, so it's currently linear. I can make it a log color scale, or I can make it a square root color scale.
Ooh.
The square root color scale is quite often very useful.
Mm-hmm.
What I generally do with the data once I've got it fitted, I suppose, is I generally export it as a 32-bit TIFF. Mm-hmm. And I'm converting it, so I don't know if you saw that bit, but I exported in units, which is called areal density, mm-hmm. which is in nanograms per square centimeter. So because I don't necessarily have a 100% handle on the thickness and the density in Z, mm-hmm. not element, but sample Z, I can't actually convert reliably to parts per million unless I know that perfectly. So if we get back to a couple of the visualizations, something that we might want to do is first of all just do an idiot check and make sure that things look right. Like, do we have some of these elements in here, for instance? Or is it just rubbish?
Yeah.
There are a couple of windows which are useful. One of them is just a 3-element RGB image, and we can just show, for instance, calcium versus whatever we want, really. Strontium, rubidium, doesn't really matter, but we can just show 3 overlays of things.
Yep.
And see where they are in space, and we can change the displayed concentrations here. This is linked, so if I go here and I can change it here as well, and we'll change it over there. Yeah. Another thing that then I can do is something that's quite interesting and useful and gets back to what you were saying, is element associations. And this is just plotting concentration versus concentration. So if I go to background, I can say this is where I have a low counts in the background, and this is where I have a high counts. I can change the color scaling on that just to highlight the low counts a bit better. And I can just select these, so that I can select these high values here, and I can go analyze that, and it shows me, I don't know if you can see, but in some of these bright spots are now green. If I select a bit more from that, you can see they come out a bit more green.
Yep.
And we say this looks like now we have selected those spots that were in our data. Now we have a roundabout way of getting this. I've got something called image regions here, and I'll just clear that entirely. And whenever I click on analyze here, it pops up with a new region. And it says the image that I've selected here is back, for instance. I'll go back to what I was doing there, and I'll grab that. It also tries to show us the percentages of different elements we've got in this.
Cool.
You can see the quantification is not super good because we've got 620% iron. So this is most likely related to the Q value we put back down here.
But very quickly you were able to identify spatially where those dodgy spectra were and potentially include them.
Yeah. What I can do now is I can select either an individual detector element and get the spectra, or I can get the whole array. And now I can put this EVT button, which gives me, first of all, a region file, which saves where all these green spots are. And so I'll save that. And then it's asking me for a spec file, which is the spectrum that we fitted down here. And so I'm now going to save that. And what it now does is sometimes takes quite a while, but now it's extracting the spectrum just from those regions. So this takes a little while. This goes all the way back to the raw data files that we put in up here that we collected, and goes back and finds wherever we have this X and Y position, and it pulls out the spectra. And now I can analyze that separately.
Right.
Once this is
very
done,
cool.
Yeah. So this is how we identify something that might be in a uniformly negligible concentration, but yet has small dots of high concentration. So we might have in the bulk, 1 part per trillion, but it might all be concentrated at quite high concentrations in very small areas.
Yep, which I guess is one of the unique problems with microXRF, but also an advantage in that you can find these things, but in order to generate these quantitative maps, you need to locate them. Yeah,
you need to find them, and of course, this is what a small plug. This is what the Australian synchrotron does well, is we can get such large maps that you can then go and dig in later down the track. So, of course, if you were just looking at a small area, you might very well miss these small dots.
Yeah. That's loading. I'm just wondering, you've got a few different windows up there, and they were linked in the sense that you could change the thresholding in detail on your main, and that would change your RGB image. Maybe windows. Can you link other functions? For example, if you have a cursor up there or a polygon or something,
Other things are linked. For instance, if I want to, I don't know if it'll allow me to do it, but here I've got something where it says distance, but I can also select an area on this one, and it's not going to let me do it because that's happening, and that will show up on this RGB one as well.
Okay, cool. So they're selection tools, are they? In that
yeah.
little...
So here's so I can just use it as a spline, for instance, or a box, or a circle, for instance.
Which of those do you find most useful?
We generally use. I generally use box most often, which we actually use to select the box, and then we can. Hang on, I'm just going to skip remaining off that because it will be here forever otherwise. With the box, I can draw a box on this one, whatever it's doing. Maybe I can't. Yeah, okay, we got it back. No, maybe I have to clear that first.
So I notice there are a few bugs with this software.
There's a lot of bugs. I suppose it's written by one person who does it. But anyway, here it's got the positions of the data in it. Hang on, I had a box there. So it wouldn't let me draw another one. There's actually a box here. Here we go. So this actually encodes, if we can see now, we've got the box size, and then this window down here, but I have to go back into the box. So it shows me the box size in actual units, and it's also got the origin, which is the origin of the stages. So this is encoding the positions of the sample. So we actually use this like we did here, where we took a very large overview, and then if I want to take a smaller view of this at higher resolution or higher dwell, then I can take the numbers of this box and program it straight into the scanning stages and redo that area.
So I've noticed you can fairly rapidly flick between different maps of different elements.
Yes.
If you wanted to pull up, say, a calcium map and maybe a titanium map, for example, side by side, and then use your cursor to select or just indicate a certain region, could you do that and link between the two views?
The way to do that is with this guy here, and you see the boxes. So if I wanted to show titanium and something else.
So you would just fiddle with the thresholds until it was clear that you were on the same grain, or whatever it was.
Yeah, if I wanted to find something that was rich in calcium and titanium, for instance, I could go make sure I'm showing all my calcium really brightly, go to titanium and really highlight that, and then I can just select the box, and I've got to move this one, and you can see the other box changes with that.
All right, what else is in the display drop down up there that might be interesting?
Here? There's a lot of stuff that is designed more for post-processing stuff, which I don't typically use, because I generally do it in outside program. There are things like PCA that you can do. I don't generally use it. I find it counterintuitive to do it in GeoPIXE. Some people like to do everything in GeoPIXE. I like to get quantitative images out of GeoPIXE.
Right.
If we go to this spectrum display, this is what we pulled out of that data before.
Yeah.
The background points. And I've got my spectrum fit again, and I can now just fit one to that. And it shows here we don't have a lot of counts. I probably should have let it go for longer.
Looks like a reasonably good fit, though. What do you think was the problem with those?
It looks reasonably good. I'm not sure what the problem was, but I think if we let it go for longer, we would probably see something where we've missed an element along the way somewhere.
Yep.
But it does look relatively good. Maybe there's something here that we've missed. You can see if we look in. Here there's a bump in this that we haven't fitted. So our fit is the red, which dips down where we go up here.
Yep.
So it could be...
Use those little buttons down there, I've noticed, to manipulate the spectrum window. Can you sort of use your mouse wheel or anything like that?
No, you've got the sliders here, and you've got shrink and expand and widen and full.
Yep.
And I just use shrink and expand. Full just shows you the full spectrum. And shrink makes it smaller, but it can't because it's showing all of it. Expand makes it wider. For some reason, they're really buggy.
Yeah. So if you could, question for you, if you could add any functionality or fix any bugs with this software, what would that be?
I would, apart from just removing the stuff that I never use.
So
the main bugs that it has, I suppose, are that it seems to want to make up new folders and not remember where you are.
Mm-hmm.
And it's just a lot of accounting that misses the mark somewhere along the way.
Right. Would you say having so many options for so many different applications and so many different power users makes it difficult for you to navigate through it?
I think it makes it very difficult for new users to navigate through, yes. Almost impossible. Yeah. Unfortunately. I can see where the problem with this spectrum is. We've actually, there's a couple of these peaks here which look like there's something else in there, and it would probably be something like, not quite.
We're sort of running
that
time.
guy.
I wonder, is there anything that we've missed?
I don't think so. So it was hafnium that we were missing.
Oh, interesting.
Yeah, so you can see now it's fitted a lot better through here. Yeah.
So it's sort of, would you say the peak fitting is at the heart of what happens. Everything sort of revolves around fitting those peaks and figuring out what elements you have and where.
Yeah, and then using the tools where you're extracting spectrum from sub areas to refit to find other stuff.
Yep.
I think that's where the power lies, and that it does it all very quickly and very accurately.
Yeah.
And you can imagine if you have a spectrum like this, you would never find hafnium doing a region of interest fit on this.
Yep. Cool. Okay. We might leave it there then, because we don't generate a file that's too long. Thank you very much for running through that.
Thank you. There's a lot of bugs and errors and fluff and stuff, but the heart of it is quite simple.
All right. Well, I guess we'll leave it there, and good luck to future GeoPIXE users.
Yes, that's right. Okay, I'll stop this recording now.
Yeah. Thanks. That's awesome. That'll be really useful for